Hello and welcome to this video on complex numbers as part of our quadratics unit in Algebra 2. Let's start by talking about square roots and how they relate to an imaginary number. So pure imaginary numbers are the square root of a negative number. So basically, the square root of -1 is defined as being a pure imaginary unit called I. We will use the variable I to represent imaginary units of imaginary numbers. Now, when you have non-negative real numbers like a and b, the square root of a times b is equal to the square root of a times the square root of b. So you can separate them, take their square roots, and multiply, but you can only do that for real numbers. And also you can do the quotient, you can do the square root of a over b or the square root of a over the square root of b, just remembering the denominator cannot be 0. The imaginary unit I is defined to have the property such that I squared equals -1 or the square root of -1 is I. Simplified square root expressions do not have radicals in the denominator. So any number remaining under the square root has no perfect square factor other than 1. Okay, so given that, let's try a few examples that you need to know how to do. Simplifying the square root of -48. Well, we can think of that as being the square root of -1 times 48. That square root of -1 can come out as I, and the 48, we make our factor tree to look for factors. So I can bring out a 4. So I bring out an I bring out a 4. That's a 4I root 3. And that would be the answer to the first one. The second one, square root of -63. Same deal. The negative comes out as an I. 63 is 9 times 7, and 9 is 3 times 3. So we can bring out a 3 as well, and a 7 is left inside. So 3I root 7 would be how that would be read. Under example 2, we're doing some more simplifying, but here we don't have a square root of a negative. We have a -3i and a 4i. We can multiply those together kind of like, just like regular variables. -12i squared. But you have to remember that I squared is -1. So your final answer would be 12. For part B, we have to be careful about how we do this, because if we do this two different ways, we get two different answers. One of the ways I could do it is to simplify first and call this one I root 3. And then this one would be I root 15. Okay, if we do it that way, then we get I squared root 45. I squared is -1, and root 45 is 3 root 5. So 3 times -1 would be -3, and then the 5 would be left inside the radical. If we do this another way and multiply the radicals together first, we get square root of 45, because the negative times the negative makes a positive. And then if we look at 9 and 5 and 3 and 3, we get 3 root 5. So the question is, which one of these answers is correct? Well, if you go back up to the top of the notes and you pay close attention to this sentence, this property of if you have two numbers multiplied, making it the square root of the product of them, so writing a product of square roots as a square root of product, only works for real numbers. In number 2b, these are not real numbers, so we cannot use that property on it. So we cannot do it this way. This is the correct answer, because square root of a times square root of b equals square root of ab only works for real numbers. In other words, every complex number is either real or imaginary, and these are imaginary numbers, so this property does not work for imaginary numbers. Okay, Example 3. We are going to solve this equation. Well, x squared is equal to negative 5 if you subtract 5 on both sides. And then we need to square root both sides. Well, from what I'm going to explain over here, it's going to be true that the square root of x squared is absolute value of x. So I'm going to explain why. Let's picture doing the square root of x squared if x equals both a positive or a negative number. So let's say x is 3. So that could be 3 squared. And when I follow the order of operations, 3 squared is 9, and the square root of 9 is 3. So it looks like the square and the square root just cancel out. But what if x is negative 3 instead of positive 3? Well, I get the square root of negative 3 times negative 3 is 9. I still get 3. So whether my x value is greater than or less than 0, whether it's positive or negative, I'm going to get a positive. The only tool we have for that in mathematics of saying whether the inside is negative, positive, or negative, we get a positive, is the absolute value symbol. So we have to say the square root of something squared is always going to be the positive value, because once you square a negative, it turns positive. The square root of negative 5 is I root 5, because you bring out the negative 1 as an I, then we have root 5. Now we know two values of x that are going to have the value I root 5 when we take the absolute value. Either positive I root 5 when we take the absolute value is going to be I root 5, or negative. So absolute value of I root 5 equals I root 5. Absolute value of negative I root 5 equals I root 5. So either way, it could be positive or negative, absolute, the x value. So we're going to say x equals plus or minus I root 5. So whenever you have to take the square root of x squared, you can assume that it's going to be plus or minus the square root of the number on the right. I know you did the square root in Algebra 1, but you probably didn't understand or maybe not explained why in terms of absolute value. Just don't get that confused with the following. The square root of 4 is just 2. It's not 2 or negative 2, because you are not taking the square root of x squared. You're just doing what's called the principal square root, not negative 2. Okay, so we have now finished solving that problem and thoroughly explaining it. Operations on complex numbers. How do you add, subtract, multiply, and divide with complex numbers? Well, if you add and subtract and multiply, basically you can just treat it like a variable situation and work it out as variables. And then in the end, you can take a I squared and put in a negative 1. So treat like regular variables. Then sub in I squared equals negative 1. So let's work a couple of examples about that, and then we'll come back and talk about complex conjugates. All right, so we're going to simplify 6 plus I plus 4 minus 5I. So we're just going to combine like terms. Get rid of those parentheses. 6 plus 4 is 10. Oh, wait a minute. We're going to have a negative because we have a positive 1I and a negative 5I. That's negative 4I. This is called a complex number. It's complex because it has a real part and an imaginary part. This is called the real part of the complex number. This is called the imaginary. And unlike with traditional algebraic expressions, we don't really write it in standard form. The standard form for the imaginary and real complex number has the I at the end instead of putting the variable before the constant term. All right, the next one, 8 plus 3I, got to distribute that negative. 8 minus 6 is 2, and 3I plus 2I is 5I. No I squareds there to worry about. We will get them on the next one, though. All right, so we get a FOIL here. 2 times negative 4 is negative 8. 2 times positive 2i is plus 4i squared. Negative 5i times negative 4 is positive 20i. Oh, wait a minute. This isn't I squared. This is just I. I'm sorry. 2 times 2i is 4i, not 4i squared. Negative times negative is positive 20i. Now we get our I squared. Negative 5i times positive 2i is negative 10i squared. Now, anywhere we have an I squared, we have to substitute a negative 1. So I'm going to have negative 8 plus 24i plus 10, which means we're going to have 2 plus 24i. So that is that one. All right, example 4, we have to talk about complex conjugates. We cannot have I in the denominator of a rational expression any more than we like to have a square root in the denominator or 0 in the denominator. So what we are going to do is use the idea of a difference of squares to make the i's on the bottom cancel out. And that is basically what we call a conjugate. So if you have a plus bi, a minus bi are complex conjugates. The product of complex conjugates is always a real number. All right, let's take a look at that. So I'm going to multiply this by 2 minus 3i over 2 minus 3i, the conjugate of the denominator. We will end up with just a positive or negative real number now. And you keep in mind that when we are multiplying by this fraction, we are actually multiplying by a value of 1. So we're not changing the value of the overall fraction that was our original fraction. We are just making it look in a different form. So I'm going to have to FOIL on the top and FOIL on the bottom. So I'm going to do 3 times 2. That's going to give me 6. 3 times negative 3i. Negative I times 2. And negative I times 3i. FOIL the bottom. 2 times 2. 2 times negative 3i. 3i times 2. And 3i times negative 3i. We can see these I terms will cancel out. And then for the 9i squared, I'm going to plug in a negative 1 for the I squared. So, I'm also going to plug in a negative 1 for the I squared on the top. So the top is 6 minus 11i plus 3 times negative 1 is minus 3. And the bottom is 4 plus 9 when I plug in the negative 1 for the I squared on that. So 6 minus 3 is 3. So it's 3 minus 11i over 13. Now they may want you, or especially if it's a multiple choice, they may want you to write it with the real and the imaginary components separated. So this could also have the fraction split up, 3 over 13 minus 11i over 13. Or minus 11 over 13i. All right, so we've got that one done. This last problem I just added this year because sometimes it would confuse people in the assignment. Example 4 here. So I'm just going to go over it now. It says find the value of a and b that makes the equation true. Well, if you just think about that this is the real part and this is the real part and they have to be equal, so a has to be 4. Okay. And then this is the imaginary part and this is the imaginary part. So 4b has to equal negative 12. So b has to equal negative 3. All done. Now you can actually write them out as equations if you want to. You can say 20 has to equal 5a and you can solve it to get a equals 4. And you can say negative 12 has to equal 4b. You divide to solve it. B equals negative 3. You can actually do it that way too if you prefer, or you can just do it in your head if the equation is simple enough. All right, the third and final page of our notes deals with 2 topics, powers of I and then an application problem in electrical engineering, which does use imaginary numbers. Okay, when asked to find a power of I, you should start by calculating the first four powers of I. All right, if I do I to the zero is is 1. Anything to a zero power is 1 from our old exponent rules. I to the first power is I, and I squared is -1 from the definition of an imaginary number. Now, to get I to the third, we know that that can be looked at as being I to the first times I to the second. That way I can just previously multiply two previous ones. And so when I do that, that gives me -I. Now, what we're going to notice is that these first four repeat over and over again. If I think of I to the fourth as being I squared times I squared, that means I can multiply -1 times -1 and I'll get 1. So it's going to start repeating over and over again. I to the fifth could be I to the fourth times I to the first. I to the fourth times I to the first. 1 times I is 1I or just I to the sixth can be I to the third times I to the third. So -I times -I is -I squared. -I times -I is -I squared. And since I squared is -1, oops, I squared is -1, it's -1 times -1, which is 1, but that's not right. I'm thinking wrong. I to the sixth is I to the third times I to the third. Oh, okay. I'm not going to do it that way. I'm going to do it this way. Sorry, I forgot about that imaginary component. I to the sixth. Let's do I to the fifth times 1. I to the fifth times I to the 1 equals I to the sixth, which would be I times I, which would be I squared, which would be -1. Okay, that's better. I to the seventh. All right, I to the 7, I'm going to think of that as being I to the fourth times I to the third, which is going to be I to the fourth is 1. I to the third is -I, so I get -I. My point in doing this is just showing you that it just continues to repeat. So all you need to do is the first four of them if you forget, because I don't expect you to memorize this, but it's pretty quick to do the first four. And then all you have to do is take the exponent of I that you are asked to calculate, divide that exponent by the value of 4, because the four first ones keep repeating. The remainder indicates your answer. So what I'm going to do here is the first one is I to the 23rd. If I do 24, or 23rd, I'm sorry, divided by 4, I get 5, and the remainder is 3. That means it's going to equal I to the third, which is -I from right here. If I want I to the 49th, I divide 49 by 4. The remainder is 1. So I to the 49th is the same as I to the first, which is I. So divide it by 4 and use the first four, 0, 1, 2, 3 remainders. Your remainder will either be 0, 1, 2, or 3, and that will be the equivalent. So that's a nice, easy way to do that. All right, the last problem here in our notes. Imaginary numbers are commonly used in electrical engineering. That is the only actual application I know for them besides quadratics when we do them like a mathematical application. A common formula that is used for electrical circuits in this field is given below. Okay, V equals C times I. V is the voltage in volts, that's the units. C is the current in amps, that's the units. I is the impedance in ohms. Impedance has to do with how much the wire impedes or resists an electrical current going through it. And that's all I know about electrical engineering. Usually you will have to multiply or divide these numbers to answer the question. You'll plug in two things and solve for the third. So V equals CI. The voltage in a current or in a circuit with a current of 2 minus 4J. So that's going to go in for C because it's the current in amps. And an impedance of this many ohms, that's the I. So I am going to plug in what I know and solve for what I don't know. We don't know V. They asked us to find the voltage. The current is 2 minus 4J. The ohms is 3 minus 2J, which means this one I'm going to FOIL out. And whenever you're doing these problems, the J's or I's or K's or H's or whatever variable they use is their imaginary unit. So J is equal to the square root of negative, is the imaginary unit. Square root of -1. J is the same as I, the imaginary number here. So FOIL, minus 4J minus 12J minus 8J squared, and we're going to plug in a -1 for that. 6 minus 16J minus 8. So -2 minus 16J volts is how many volts is going through that wire. Okay, so that is the end of our lesson on imaginary numbers. Join us next time when we are going to start working with the quadratic formula and deriving it and applying it to find roots, now that we can put our answers in terms of imaginary numbers.